Hello, everybody, and welcome back to Geography 340 Climatology. I am Dr. Zach Hilgendorf. Today, we're going to be talking about energy. Now, in the last few lectures, we talked about the composition and structure of the atmosphere. We're going to be considering a few of those different things in this lecture as well, but the primary focus here is going to be on the different types of energy and the different laws in which we understand the transfer of energy within our Earth systems. So first off, what is energy? Well, really simply, it's the ability or capacity to do work. Every object has potential or kinetic energy, and basically that just says that every object, myself, you, a ball rolling down a hill, the sun, etc., all has energy within it. So there are a couple different types of energy. We have kinetic and potential energy. So start off here with potential energy. It's just the stored energy and the energy of position. So, we look at the example figures here, a reservoir behind an electric or a hydroelectric dam, a high pressure scenario, excuse me, different types of chemical or potential energy, and then food. So pressure energy is one that we're interested in, and that is essentially just the energy in or of a fluid due to the applied pressure as force per area. We have a fun relationship known as the Bernoulli principle, which derives pressure energy and relates it to potential energy. We're going to see in the next slide, but let's first talk about kinetic energy. So kinetic energy includes the motion of waves, electrons, atoms, molecules, substances, and objects. And we'll often think of it as radiant energy, the electromagnetic energy that travels in transverse waves. Radiant energy includes the visible light spectrum, X-rays, gamma rays, and radio waves. Light is one type of radiant energy. Sunshine is also radiant energy, which provides fuel and warmth to make life on our planet possible. Next, we move into thermal energy. Thermal energy, or heat, is the energy that comes from the movement of atoms and molecules in a substance. Heat increases when these particles move faster. One example of this is geothermal energy, which is the thermal energy within our planet, within Earth. And then finally, we move into mechanical energy. Mechanical energy is the energy stored in objects by tension. So compressed springs and rubber bands that are stretched are examples of stored mechanical energy. So here is our Bernoulli principle. We're not really going to be focusing too much on Bernoulli. This is more for physics or fluid dynamics courses. But simply put, it's a way to compare energy per unit volume before and energy per unit volume after. A lot of times you see this in this example with flow through a pipe or the flow of fluid through a pipe. We care a lot about this in aeolian transport or wind transport of sediment. We care a lot about this in fluids or fluvial systems or river systems as well. The often cited example, if we see in the box on the right there, of the Bernoulli equation or Bernoulli effect is the reduction in pressure which occurs when the fluid speed increases. So here we see P1 on the left in our bottom little pipe diagram there, and P2. So we're seeing an increase in fluid speed because we're restricting the area through which that fluid can flow, but it has to flow, the same volume is flowing through the pipe. So in order to get that volume through the pipe, you have to increase the speed. So when you have an increase in fluid speed, you have a decrease in internal pressure. So if we look on the left there, on the very top in our equation, we see P1, so the pressure at 0.1, plus rho v, so density times velocity. So rho is often designated as density. So rho is that is the Greek P symbol that you're seeing there in that second term. You square that, and then you add rho g, which is the gravitational acceleration constant, so 9.81 meters per second squared, times the height differential of your whatever you're looking at. And then you do the same thing on the other side, and you look at how those differ, and you can understand better the pressure within that system. So energy is, as we said, a measurable quantity. And really all it signifies is a calorie. It's signified by a calorie. And what a calorie is the thermal energy needed to raise the temperature of 1 gram of water 1 degree Celsius. And we see that all around us, right? We see it on food. Usually on food, it's expressed as a kilocalorie, kcal. So if we remember our prefixes, just 1,000 times more, right? So 1,000 calories. It's also represented by joules in some cases. So 1 calorie is equal to about 4.19 joules, and likewise, 1 joule is equal to about 0.239 calories. And like I said, it's everywhere. And what it really means is, in the food sense, it's kind of a how much potential, like what energy is within whatever it is that we're consuming per size, per serving size. And now we need to get into some laws, because energy is semi-predictable in what it does in a lot of ways, and we've come up with laws to express these relationships. So the first one is the first law of thermodynamics. So the first law of thermodynamics is essentially an application of the conservation of equation principle to heat and thermodynamic processes. And it says simply the change in internal energy of a system is equal to the heat added to the system minus the work done by the system. So we're looking at the expenditure of energy, heat, thermal energy, and the change in internal heat added to the system versus the work done by the system. So this first law kind of sets up this conservation of energy principle. And if you recall a number of lectures back, we talked about the conservation of matter. Can be neither created nor destroyed. We talked about previously. So here energy has to go through this kind of relationship of energy in, energy out. The second law of thermodynamics says that energy always flows spontaneously away from being concentrated in one place, becoming dispersed and spread out, unless something keeps it from doing so. So let's look at an example here that might make sense. A casserole. In this case, it looks delicious, ham and cheese and macaroni and all this good stuff. And it's probably been sitting in an oven at, 425 for probably 40 minutes or so. And that oven is heating up this previously cool body, this previously cool object. And as it's being heated up, energy is being imparted within this substance, this food. And it's also giving off its own radiant energy as well. So that thermal energy transfer, as we see it here, in certain areas, it's non-consistent. Otherwise, the entire top would be the same color brown. So it's randomly distributed or dispersed throughout the body of this form. And if we think of the fact that that top is open and underneath of it is everything is encased by this glass shell, it's being preferentially dispersed through the top of this object. That's why you don't see it brown as much on the sides as you do on the top, for example. So a quick corollary to that is thermal energy always flows spontaneously from warmer to colder environments or parcels, unless something keeps it from doing so. And this is going to be really, really useful to us as we consider pressure systems, climatological patterns, and how temperature drives these weather patterns, right? This is a climate course. We're really interested in knowing these aspects of the world. And the second law of thermodynamics helps us understand that. So let's go ahead and talk about these mechanisms of thermal energy transfer that we've been talking about here. So we're going to use a really popular example, a pot of boiling water being heated by an electric coil on a stovetop. So we've got 3 different types of energy that we're going to be talking about on this one. We've got conduction. So conduction transfers heat via direct molecular collision. An area of greater kinetic energy will transfer thermal energy to an area of lower kinetic energy. Higher speed particles will collide with slower speed particles, and the solar speed particles will increase in kinetic energy as a result. So conduction is the most common form of heat transfer and occurs through physical contact. In this case, we have the bottom of our pan and we have this electric coil. Heat is being directly transferred from the electric coil to this pot, which is touching it on the bottom of the pot. Next, we've got a fluid such as air or liquid is heated and then travels away from the source. It carries thermal energy along with it. This type of heat transfer is called convection. So the fluid above a hot surface expands, becomes less dense, and then rises. Next, we've got radiation. So thermal radiation generates from the emission of electromagnetic waves. So these waves carry the energy away from the emitting object. Radiation occurs through a vacuum or any transparent medium, either solid or fluid. Thermal radiation is the direct result of random movements of atoms and molecules in the matter. Movement of the charged protons and electrons results in the emission of electromagnetic radiation. So this object is radiating heat. So from the bottom, we have conduction. Heat's being transferred from these hot coils directly to the pot. Now, through the top, you've kind of got this opening. So through convection, heat is being taken away and dispersed from the top of this object. And then radiation, it's being radiated and emitting from the side. So these are all kind of what we call radiant energies. So next, we'll talk about what radiant energy is. So what's radiant energy? We've kind of talked about this now a couple of different times. Well, radiant energy is a form of energy emitted by all matter. It's a form of energy that can travel through a vacuum at the speed of light, which is really, really crucial if you have something that's being heated by the sun, for example. But what is it? Well, it's either a stream of particles of pure energy, which we also call photons, or it's a stream of coupled oscillating electric and magnetic fields, what we would call electromagnetic waves. And something that we're going to focus on now is electromagnetic radiation, or EMR for short. So here's just an example of kind of the travel of electromagnetic energy, for example. We have our amplitude, the wave height of this emitted energy. So typically you see it traveling as a wave. Light travels as a wave. And then you've got your wavelength. So based on the amplitude and your wavelength, you have different functions of light. And that gives us the range of possible electromagnetic wavelengths. And let's look at something we should all understand or all be at least aware of. It's the electromagnetic spectrum. Here it is in all of its glory. So we have a few things to call out. First off, this is expressed in micrometers. So that's the dominant unit we use to describe the electromagnetic spectrum. If we are to this side of, well, this side for y'all, the stage left, I suppose, we have higher energy, shorter wavelength, and higher frequency. So we're looking at gamma rays and X-rays and ultraviolet waves. So if you look at that example on the bottom, they're underneath the electromagnetic, different types of electromagnetic energy. You see kind of the oscillatory waves there that are thinner and more frequent to the left. They're higher energy and they spread out as you go towards the right, where it's lower energy with longer wavelengths and lower frequency. So here we're thinking of radio waves, microwaves, far infrared waves, and thermal energy or thermal infrared. So those are kind of the dominant ones that we really think about when we think of kind of our lower energy spectrum. If we look at the ultraviolet, something we care a lot about through what our sun emits and what we absorb as humans. We also look at the the visible light spectrum there, which goes between 0.4 and 0.7 micrometers. So the higher energy are your violets, your blues, your greens. The lower energy are what we see rendered as yellows and oranges and reds. Here is another group, the near infrared through the far infrared, that we really care about because, one, it's something that plants and photosynthetic beings and organisms really care about, but thermal energy is transmitted in this as well. Now, if we look at our ultraviolet, we have UVC, which is around 100 to 280 nanometers. We have UVB, which is around 280 to 315 nanometers. And then we have UVA, which is between 315 and 400 nanometers. On the near infrared side of things, that is roughly between 0.7 and 4 micrometers. Thermal infrared is between 4 and 100 micrometers. And these are kind of, as humans, the ones we really pay attention to and we really care about, especially those in the visible light spectrum, which is really just a small sliver. Now we see in the visible light, but other creatures, bugs, predators of many different types, see in different types of light than we do. But as far as the electromagnetic spectrum goes, these are the ones we really care about. So everything from about ultraviolet through the far infrared. So let's look at some of our electromagnetic radiation laws. There's going to be 4 that we're going to really focus on today. Law 1 is simply the emission of radiation. All substances emit radiation as long as their temperature is above absolute zero, which if you're looking at it in Celsius, it's negative 273.15 degrees Celsius. If you look at it in Kelvin, it's 0 degrees Kelvin. So that's the first law. Pretty simple. Second law, and this is where it gets a little bit tougher, or more complicated at least, is what we would call the black body and Planck function concept. So the sun is very similar to what we would call an ideal emitter or black body. It is emitting radiation and emitting electromagnetic radiation away. So the definition of a black body, a hypothetical object that absorbs all of the radiation that strikes it. It also emits radiation, energy flux, at a maximum rate for its given temperature. So basically it's taking in everything and giving off as much as it possibly can. So black bodies exhibit a defined relationship between the intensity of radiation energy, which is the amount of radiation flux that they give off, and the wavelength of that radiation. So this relationship is called the Planck function. So Planck, Max Planck, in 1900 postulated that electromagnetic energy is emitted by discrete portions or quants rather than continuously. So light can be considered not only as a wave-like entity, but also as a particle or photon with the energy given by the Planck's law, or by Planck's law, which we can see here. So an easy way to remember the black body and Planck function concepts are that shorter the wavelength, the greater the intensity of that energy flux. So Planck's law simply says that E, or energy, is equal to hc divided by lambda. So where h is the Planck's constant, so 6.52 times 10 to the negative 34th joule seconds. C is the speed of light, so 3 times 10 to the 8th meters per second. And then lambda is your wavelength. So the emission rate, so moving into our third law, is the Stefan-Boltzmann law. So the emission rate of electromagnetic radiation is directly related to the temperature of the matter emitting it. Here's our equation. So the total amount of radiation given off is actually proportional to the 4th power of its absolute temperature. So if we look here, we'll see a few different things. So let me advance this here just a couple. So we see at the left, that's electromagnetic radiation emission rate, or I, in watts per meter squared. The T is, or our big T here is temperature in kelvins. And at 0 degrees Celsius, it's 273.15 kelvins. At 100 degrees Celsius, it's 373.15 kelvins, just to give you an idea of kind of that conversion rate. So here we see sigma, and And sigma is the Stefan-Boltzmann constant. So this law links the total amount of energy flux that's emitted by a black body to the body's temperature. So in this case, this is just a constant that Stefan-Boltzmann came up with, which we use as 5.67 times 10 to the negative 8th watts per Kelvin meter squared. And there's a proviso here. This strictly applies only to black bodies. This is kind of a limit of this law. But fortunately for us, we like to look at things in idealized situations. So epsilon, as we see here, it's not in the equation. It is formally, but it's not in the equation that we're going to care about here. Epsilon is emissivity. But we typically assume we're working with a perfect black body. So this is always going to equal 1. It's kind of a 0 to 1 scale. So here, we're not going to really take into account a non-perfect system. So in this case, don't worry about emissivity. It's really just 1. It equals 1 in this case, in the way that we're going to use it. So we can kind of ignore it in this equation. So in this case, and also with the Stefan-Boltzmann law, it's important to note that the hotter the body, the much greater the amount of energy flux or radiation. As you can see, we're raising temperature to the 4th power here. So it's kind of a rapidly rising relationship between increasing temperature and increasing electromagnetic radiation emission rate. So this concept's important because it means that the amount of radiation given off by a body is very sensitive to temperature. Small changes in temperature can lead to big changes in the amount of radiation given off. Moving on to our 4th law, temperature and wavelength. As substances get hotter, the wavelength at which radiation is emitted will become shorter. This is also something we call the Wien's displacement law. So this says that the wavelength of maximum electromagnetic radiation emission is displaced to shorter values as the temperature of matter increases. So here's the equation. So lambda max is equal to B over T. Lambda max is the wavelength in the spectrum at which the energy peak occurs. B is Wien's displacement constant, which equals 2,898 micrometers Kelvin. And T is equal to the absolute temperature of the body that we're examining in Kelvin. You can see those here. So basically what we're saying here is that the hotter the body, the shorter the wavelength, and the cooler the body, the longer the wavelength. So this is actually a pretty important concept for us because it means that hot objects, very hot objects like the sun that radiate like black bodies will radiate the maximum amount of energy at shorter wavelengths. Cooler bodies will radiate most of their energy at the longer wavelengths. So just as a quick recap for what we kind of talked about. So in this little lecture, we looked at what is energy. We talked about the first and second laws of thermodynamics briefly. We touched on the emission of radiation from an object, the black body and Planck function concepts, the Stefan-Boltzmann law, and Wien's displacement law. So from here, we're going to start going into solar radiation, Earth-Sun geometry relationships, and the seasons. So we'll stay tuned and we'll be heading there next. Thanks.